Our next speaker is Tyler Robinson. He's at the University of Arizona, and his talk is on rfast.
Great. Thanks, Ted. Thank you so much, Natasha, for that review and all of the insight on your own approach to open source code. Um, so I should preface this with saying that I've been at home for the last couple days with a very sick toddler who may burst in at any moment. And that's if Sleeping Beauty doesn't keep up her end of the bargain. So let's hope that he stays entertained. So I want to talk today about an open source tool that a postdoctoral scholar working with myself, Arnold Salvador, and I recently had a manuscript accepted on. So I'll talk a little bit about the history of this tool, why it exists, and what you might be able to use it for. As I've noted down here, if you want to look at the description paper, see some example applications of the tool. It's up on the archive, and then also the software itself is up on GitHub. So a bit of motivation here, which is really the origin story for the software, dates back to the time that I spent on the HABEC Science and Technology Definition team. And I had a lot of fun on the HABEC Science and Technology Definition team. And one of the great aspects of being on the SCDT was the rapid back and forth between the scientists and the technologists and the engineers that were working to design the concept. And oftentimes an exchange would kind of go something like this, where the scientists had said, we would really like the instrument to be able to behave this way or to take measurements in this wavelength range. The engineers would look into it and they come back to us and say, sorry, there's no way in hell that we could ever imagine doing that. Could you actually maybe shrink the wavelength range by a lot and still do your science? And I use the scientist would say, maybe let me investigate. And in those circumstances, I was finding that some of the tools that I was typically using that had long run times just weren't well adapted to this kind of rapid environment where we needed to quickly assess feasibility of certain science themes or feasibility of certain instrumentation setups. Um, Similarly, when you're doing your own feasibility studies, sometimes you don't need to be ultra detailed and kind of a first pass that is aiming to assess whether or not an idea that you've had could work out. And so somewhere in your brain, you might think, I wonder if there's any way that HABEX or LUVOIR or Habitable Worlds Observatory or JWST could even detect this thing that I've been thinking about. And you don't want to spend a week on a cluster doing some kind of sophisticated model to understand feasibility. Instead, you might want to just do something quickly to see if feasibility is even on the table. Um, and so uh, some material dating back to my HABEX days, I had put together a tool whose job it was to enable rapid studies of atmospheric inference. And so it went from quickly generating a simulated observation. And so you can see some data points here that are a simulated observation for potentially an exo-Earth there in gray, to doing atmospheric inference on it, all in a pretty carefree setup. And so over here on the left, you can see that it's building up the posterior distributions as it's dancing around, trying to fit those simulated data. And in this particular circumstance, the free parameters were something like the log of the surface pressure of the planet and the log of the water vapor mixing ratio, were just a couple of example parameters that I was trying to fit for. And so to give you a few details that are kind of background on the tool that we put together, it's written in Python and it's open source. Like I said, it's up on GitHub. It has very fast radiator transfer cores that we have incorporated. It has options for the user to do the radiator transfer in 1D for kind of a diffuse 1D reflectance model. You can pixelate a globe and do 3D reflectance from a planet. You can do thermal emission. You can do thermal emission combined with 1D reflectance, and it can also handle transit spectroscopy. Just as an example of what a kind of characteristic runtime is, I get about, on a single core, 50 microseconds per isochromatic calculation, and that was for a model atmosphere that had 50 levels and was handling pressure and temperature interpolations for 8 different gas species. It includes an optional noise model for creating faux observations. And so you can generate a high fidelity forward model if you want. And then the next step can be in the pipeline. If you're interested in understanding detectability, you can apply a noise model to it. And so you could say, what would it be like if Habex observed this? You can specify spectral resolutions and band passes and noise levels at all of those different wavelengths to get simulated noise or a faux observation with simulated noise. And then if you want, the very last step can be to apply a Bayesian inference model to it. Right now we're using MC, but I'll return to that shortly. And it has a fairly, I'd like to think, easy interface for doing that inference. I've set it up to be fast so that you might be able to run it even on your desktop, or if you have access to a couple tens of cores, it runs in a time scale of hours to do the inference calculation. And part of the motivation here was kind of back in 2016, 2017, when I was gearing up for the Habex study. Some of the issues I was running into was common models that would do atmospheric inference. There was a lot of hard coding that you had to go in and do to change whenever you wanted to change your prior, or if you wanted to change the parameters that you were hoping to do atmospheric inference for, so the things you were fitting for. That often took a lot of work. And so I tried to figure out a way to get around that so that I wasn't introducing bugs to code on accident. Of course, nothing comes for free. So when I say that the radiative transfer models are super fast, you probably think, well, how do you get that speed? The reflected light and thermal emission models are really quite simple. And so that's one way that we get our speed build up. The transit transmission model is not really that simplified. So we have effectively, trimmed off a few corners to do the fast radiative transfer. As I'll show you in some slides, we've worked to validate the radiative transfer, though, to make sure that it's behaving well enough. But something that should make you maybe rest a little bit easier in the evening is that for your feasibility studies, especially when you're using this rfast tool, if you use the forward model to generate a synthetic observation and are using that same forward model to do inference on that synthetic observations, systematic issues will then tend to cancel out, and so you're less sensitive to the details of the radiative transfer. So here's a little bit of information showing off the validation. So this is compared to a line-by-line multiple scattering radiative transfer model called SMART as a common tool that I use. This is a reflectance spectrum of Earth across Habex and LUVOIR-like wavelength ranges with a fair comparison between the rfast forward model and SMART. Here it is in thermal emission, again for Earth, looking fine. Here's a comparison with the transit geometry. I'll note that the solid lines here don't have refraction, and there's reasonably good agreement between the two, showing effective transit altitude as a function of wavelength. But when you turn on refraction, you do get a little bit of a difference here in the refractive floor from the two models. That's because SMART does a full ray tracing calculation. You can't do, or at least I don't suspect that right now it's easy to do a full ray tracing calculation inside of a tool that you would want to use in an inverse setting. And so instead, we use an analytic approximation in rfast to the refraction floor. We've used it to understand how if you change the setup of your instrumentation, say if you just have optical data versus UV, optical, and infrared, thinking about Habitable Worlds Observatory at different SNRs, what kind of different constraints could you expect to get for atmospheric gases? This is for an Earth-like setup, and you can see that the upper limit that you could set on CO2 in Earth's atmosphere is sensitive to what wavelength ranges you have access to and what the SNRs are at those wavelength ranges. And in our manuscript, we also demonstrate taking actual solar system observations. And so this is a disk-integrated mid-infrared spectrum of our Earth, and we applied the inference tool to it to see how atmospheric inference unfolds when you're challenging it with real observations of planets that are stand-ins for what we hope to observe in the future, either with Habitable Worlds Observatory or the LIFE mission concept from our colleagues in Europe. I've set it up to be easy to use, and so it's just a handful of commands: generate a spectrum, add noise, set up your retrieval, and run the retrieval, and it gives you some information about timing when you run it. This is just an example of how I've managed to make, I hope, it easy for users to turn on and off different parameters that they want to infer. And so these are the different parameters that you could try to fit for when you're doing atmospheric inference. You can toggle them on and off. Is it a retrieved parameter? Do you want to apply priors in linear or in log space? Do you want those priors to be Gaussian or flat? And then what are the bounds on those priors? And so this makes it so you don't have to go in and change something hard-coded inside of the inference tool. We're of course interested in putting in more sophisticated radiative transfer that will slow it down, and so we would just like to add an option for that. And then we're also interested in expanding to other samplers. For example, we've had some students working on trying the tool out with multi-nested sampling, and that gets us a big speed up. So again, trying to push this to be something that could even run on your laptop. So to summarize, rfast is a Python-based open source tool designed to enable rapid atmospheric remote sensing studies. It was born of mission design, and I hope to continue using it in mission design scenarios. The radiative transfer cores of rfast are quite fast. They're computationally efficient, but they're simplified to enable the speedy end of rfast. And we have some example future work that we could do to improve this tool. And with that, I'll thank my funding sources, which is NASA XRP, Nexus, the Exobiology Program, Habitable Worlds Program, and I'm happy to take some questions. Thank you all.
Thanks, Tyler. Does anyone have any questions? They can raise their hand or type in the chat. While we're waiting, I would like to ask, so since you use a simplified radiative transfer core, what regimes do you find that your results differ most from other codes that maybe take longer to run?
Yep. So especially for the reflected light model, scattering and multiple scattering is always the challenge when you're simplifying radiative transfer. And so we've seen in our explorations that is certainly the case for rfast. And it's especially challenged when you've got different multiple sources of scattering. So if you've got Rayleigh scattering occurring at the same time as cloud scattering, that's an even more complicated problem. And so we've seen that scenarios where you're blending a couple different kinds of scattering do lead to systematic differences between the fast radiative transfer cores that we're using versus, say, a full physics model.